Welcome back, learners, to today's deep dive. Our mission for this session is a complete single-session revision of NISAR, along with some key spectral imagery concepts. So if you're in the armed forces, this is your complete tactical overview.
Right, yeah, glad to be here. We're going to take a very structured approach today, learners. We'll outline a top-down conceptual flow, starting right from the core radar technology all the way down to strategic field applications.
And to set the stage, just imagine looking down at Earth during the heaviest monsoon of the decade. With standard satellite cameras, all you see is just a massive blanket of storm clouds.
Which is a huge problem for continuous observation, yeah.
Exactly. But what if you had a sensor that could punch straight through that storm, through the dense forest canopy below, and actually measure the structural shifts of the soil?
It sounds like science fiction, I know, but that level of observation is exactly what we're looking at today. It completely redefines how the armed forces can interact with the environment.
So let's jump into layer one, the fundamentals.
Yeah.
We're talking about NISAR, which stands for the NASA ISRO Synthetic Aperture Radar. And to really grasp why this is such a massive leap, we should quickly contrast it with passive spectral imagery, like HISIS, for example.
Right, the hyperspectral imaging satellite. HISIS is brilliant at collecting light across the spectrum to identify materials, but as you said, it's passive. It relies entirely on sunlight.
So if there are clouds.
It's completely blocked. You can't see a thing. NISAR, on the other hand, makes its own weather, so to speak. It's the first mission ever to pack dual-frequency radar onto a single platform.
And the sources mention it gathers highly advanced polarimetric and interferometric data. Sounds great, but I definitely need a translation for those terms.
They're dense terms, yeah. Let's break them down for the learners. Interferometric simply means the satellite compares two radar images taken at different times to measure tiny shifts in the ground.
Like how tiny?
We're talking changes down to fractions of an inch. It's incredibly precise. And polarimetric means the radar waves bounce back in different orientations, which gives us the precise 3D structure of whatever they hit.
So it's not just, taking a flat photograph. It's actually feeling the texture and the volume of the ground.
Precisely. And it does this using two distinct radar bands, the L-band SAR and the S-band SAR. Think of them as two sets of eyes tuned to entirely different depths.
Okay, so how does the L-band work?
Well, the L-band uses much longer waves. Because they're physically longer, they don't get scattered by small things like leaves or rain. They penetrate deep through forest canopies, thick ice, and soil.
Oh, wow. So that deep penetration is how we measure hidden biomass or deep ground deformation.
Exactly right. Meanwhile, the S-band handles the surface level. It uses shorter waves that bounce right off the top layer, making it perfect for monitoring crops and wetlands.
Combining both depths on one platform is just wild. But I'm stuck in the logistics here. To pull off these millimeter-precise measurements globally, the hardware specs say it has a 12-meter deployable antenna.
It does. It's absolutely massive.
I mean, 12 meters is the size of a school bus. How on earth do you pack a school bus-sized antenna into a rocket?
Well, you have to. In radar technology, a larger antenna gives you a wider sweep and much higher resolution. To get it into space, that dish is folded up like an incredibly intricate piece of origami.
That brings us nicely into layer two, the mission lifecycle. So it launches folded up on a three-stage expendable rocket, the GSLV Mk2.
Correct. That's the launch phase. Once it hits orbit, we enter the deployment phase. And this is key. It doesn't just unfold the antenna. It mechanically pushes it away from the main satellite body using a 9-meter extension boom.
Oh, to isolate it from the satellite itself.
Yes, exactly. That physical separation isolates the highly sensitive antenna from the electronic noise of the main body. It keeps the radar readings crystal clear.
So we launch it, we unfold this giant boom, and then what? Does it just start mapping immediately?
Not quite. It enters a 90-day commissioning phase first. When you're measuring ground shifts down to the millimeter, your instruments have to be perfectly calibrated.
Makes total sense.
After those 90 days, it begins its 5-year science operations phase. And for the learners, the absolute heartbeat of this phase is its 12-day global coverage cycle.
Meaning it literally maps the entire Earth every 12 days. Let's transition to layer three, objectives and strategic applications. Why is that 12-day orbital heartbeat so vital for ground forces?
It all maps back to its 4 main scientific goals: tracking ground deformation, measuring biomass, monitoring agriculture and wetlands, and studying the cryosphere.
Right, and when we translate those goals into strategic applications for the armed forces, that 12-day cycle is just, it's critical tactical awareness.
Exactly. Take infrastructure stability, for example. If the ground under a vital supply bridge is shifting, NISAR catches that deformation well before a collapse.
Or for disaster mitigation, like if there's a rapid onset hazard like an oil spill, you don't have to wait days for the clouds to clear to see where it's spreading.
That's the real power here. It transforms this highly complex dual-band radar physics into actionable intelligence, totally regardless of weather.
Which is just a massive strategic advantage.
Definitely. So to give a concise chapter-level summary for our learners to close out, we started with the fundamentals, how the dual-band L and S radar penetrates different depths to capture 3D structural data. We moved through its mechanical life cycle, specifically that massive deployable boom.
Right.
And finally, we linked that 12-day global mapping orbit directly to actionable military and environmental intelligence.
That perfectly ties it all together. And before we go, I want to leave you, the learners, with a final thought to chew on. Considering NISAR's ability to see through thick storm clouds every 12 days, how might this specific capability permanently change how the armed forces strategize and execute rapid disaster relief for a sudden landslide in a remote, rain-obscured mountain region?
It's a great question to reflect on.
Definitely something to think about next time you look up at a cloudy sky. Thanks for joining us for this deep dive.